Are you able to recognize this word? What about this one? And this one? How is your brain able to interpret this data? All images are very different, yet we recognize them as the same word. The complex operations that your brain performs every day should not be taken for granted. Mimicking this phenomenon in computers is not an easy task, but not impossible. Functioning similarly to the human brain, neural networks are computing systems that collect data and interpret it using a set of calculations to produce an outcome. To explain this, let's begin with a simple question. How much will a certain item cost? To answer this question, we will need to work with multiple variables that will serve as our input. These variables can include cost of production, manufacturing time, perceived value, weight, volume, and total number in circulation. Our expected outcome will be an estimated price. These variables are called nodes, and they simply hold a value between 0 and 1. The number inside the node is called its activation. The left side will serve as the first layer in our neural network. Looking at the last layer, we want our neural network to produce one outcome node, which will be the predicted price of the item. The activation of this node will again be a value between 0 and 1 and will represent how confident the system is in the estimated cost. The higher the value, the more accurate the network is. The calculations that take place between the input nodes and output nodes will be performed in the hidden layers. The activations in one layer will determine the activations in the next layer. This is done through a process called feature engineering. Feature meaning a variable made up of other variables. Essentially, the neural network is taking the data we give it to create features through a series of calculations. Then those features are used to produce an output. So what exactly are the calculations that take place in those hidden layers? To begin, we'll assign a weight to each one of the connections made between the nodes from the first layer and a single node from the second layer. These weights begin as random numbers. Next, all activations from the first layer are used to compute a weighted sum based on the assigned weights from each connection. Computing a weighted sum can give us just about any number, but for this neural network, we want activations in the following layer to fall between the values 0 and 1. To do this, the weighted sum will be plugged into a function that condenses the real number line into a range between 0 and 1. A function that does this is called the sigmoid function. It's not always that we want the weighted sum to activate when the weighted sum is greater than 0, maybe greater than 5. That is, we want some bias to delay the triggering of the activation function. So, we can add in a number, such as -5, to the weighted sum before it goes through the sigmoid function. That additional number is called the bias. And that's just for one node. Every node in this layer is going to be connected to all the nodes from the first layer. Each connection has its own weight, and each node has some bias. This is the same for every connection made between all layers. Learning refers to tweaking the value of weights and biases, getting the neural network to work more accurately. Neural networks have a growing importance on today's world. They can be used for a multitude of things, such as voice recognition, game AI, robot navigation, image classification, and more. So next time you say, "Hey Siri," think about the complex processes that brought her to life.